In this video, we will be talking about derivatives and integrals of vector functions. But before we get into that, let's do some quick review from Calculus 1. Consider the function f of x equals 1/4 x squared plus 1 graphed below on the closed interval from 0 to 4. F of x contains the points p located at 2, 2 and q located at 4, 5. So the idea in Calculus 1 is we start off with connecting 2 points on a curve, P and Q. And if I connect these with a line, this is called the secant line. And the way that we find the slope of the secant line is by taking the y-coordinates, subtracting them, and then dividing that by the difference in the x-coordinates. The whole reason that we care about the slope of the secant line is because it tells us about the average rate of change for our function. And where we would like to get to is we would like to create the tangent line at a given point. So oftentimes what we'll do is we'll make P the fixed point and Q a changing point or a dynamic point. And so we would like to find the tangent line at P because the tangent line tells us about something that is called the instantaneous rate of change. So how do we get the slope of the tangent line? Well, here's a little review of what we would do in Calculus 1. Like I said before, I'm going to keep my p-value or my p-point fixed, and I'm going to choose some arbitrary point on my graph as well. And in this case, even though we know the ordered pair for p, I'm going to generalize this and say, let's say this x value is x, and I want the distance between my 2 points to be h. So I want the distance from here to here to be h units, meaning that I'm going to have this x value be x plus h. So that now what I'm doing is I'm taking the slope of this secant line, and notice that this is a closer point to P. And so here, this y value, that would be f of x, and this y value here would be f of x plus h. So for this particular secant line, if we wanted to find the slope of it, we'd have the slope of the secant line is equal to the y value f of x plus h minus the other y value f of x, and then over the difference in the x values, so x plus h minus x, and notice that that just simplifies to h. And recall that this thing is called the difference quotient. Now, as a reminder, our goal is to get the slope of the tangent line, which is this green line here, and the way that we can approximate it is by taking smaller and smaller values of h. And again, in Calculus 1, we learn about h going to 0, and we learn about this thing called a limit. So then we learn that the slope of our tangent line, or in other words, the instantaneous rate of change, is equal to f prime of x, our derivative function, which is equal to the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x all over h. All right, so I've taken the steps to start taking the limit definition of our derivative for this particular function that we are looking at, f of x. And I'm at the stage where now I have the limit as h approaches 0. Notice that the remaining two terms both have an h in it. I can factor those out and divide that with the h in the denominator, giving me the limit as h approaches 0 of 1/2 x plus 1/4 h. And Now I no longer have an h in the denominator, meaning that I can use direct substitution. And if I plug in h equals 0, notice that for all this work, we get that the derivative is the function 1/2 x. Now, the really nice thing that we learn about in Calculus 1 is we learn about these rules to take derivatives so that we don't have to go through this long process of evaluating a limit or the limit definition of a derivative. And for this function in particular, if I wanted to take its derivative f prime of x, I can use the power rule. If I bring the power down, that ends up giving me 1/2 because 2 times 1/4 is 1/2. And then we have x, and I decrease the power by 1, so we can get our derivative function that way. So again, I just want to reiterate, we found our derivative function f prime of x to equal 1/2 x. The reason that we care about this function is now anywhere along my original function, I can find the slope of the tangent line or the instantaneous rate of change. So let's find it where we were originally looking. So suppose this is our tangent line right here, and we'd like to find the slope of that tangent line. Because I know in this particular example, the the point P has an x value of 2, that means that I can evaluate my derivative at x equals 2, and if I simplify this, that gives me 1. So by doing that, we found the slope of the tangent line, which is also the instantaneous rate of change. And then finally, another thing that we can do is we can find the equation of the tangent line. I've provided that here in point-slope form, as well as slope-intercept form. So that is a quick overview of limits and derivatives from Calculus 1.